All right, cool. So we're going to talk about the squeeze theorem again. Uh, so the question reads, what is the limit of sine x over x as x goes to infinity? Okay. So the squeeze theorem goes like this, okay? So it's the squeeze theorem. Let's say that we're trying to find the limit as x approaches value a of a function, okay? And we cannot find that limit using conventional methods of substitution or algebraic techniques or using the conjugates. We can't find it conventionally. Well, the squeeze theorem suggests that we take our function f of x and we squeeze it. So we need to know that the range of f of x is less than or equal to, let's say, the range of h of x. Okay, so we find another function that will always be greater or equal to f of x. And we find another function that will always be less than or equal to the range of f of x, okay? So once we have this inequality set, right, if the limit of g of x and h of x as x approaches a is the same, then f of x also has that limit, okay? So if the limit of g of x as x approaches a and the limit of h of x as x approaches a both equal the same limit, then the limit of f of x as x approaches a also equals L, okay? So this is the squeeze theory, all right? This is a squeeze theory, okay? So this is a very useful theorem. If you want a proof on how the squeeze theorem works, you can search it online, but it has something to do with the fact that we're constricting and maintaining the range of f of x between two very similar functions. And if those functions have the same limit, then any function within the middle or squeezed within the middle also will have the same limit. So not only talking about f of x, there could be other functions that are also maintained within this range of functions here, and they will also have the same limit. Any function within this range will have the same limit. And the very useful thing about the squeeze theorem is that you can make g of x and h of x very simple functions that you can calculate the limit of. And if the limit equals the same, then your very complicated function in the middle, that limit will be the same. So you can bypass all those tricky techniques of using algebraic or conjugates or some unknown or some obscure method of finding that limit. Okay, so in our example here, we have the limit of sine x over x as x approaches to infinity, okay? So as x approaches to infinity of sine x over x, we have a problem here already, right? So sine x is an oscillating function. That means that it always wiggles between 1 and -1. So if we were to plug in infinity, we actually don't know what the limit is because it could be going up towards 1. But once it goes up towards 1, it starts going back towards -1. And since it's oscillating, we don't really know the limit of sine of x in general. So this is just, we don't know what the limit is, right? So using our squeeze theory, right? So let's say, first of all, that sine of x, let's squeeze it between two different functions, okay? Oops. Let's squeeze it between g of x and h of x, okay? Let's say, let's h of x equal -1, okay? So we're going to say, let's make h of x the most simple function, -1. It does not change, it's just constant. And g of x, let's make it equal to 1. All right, let's see if our inequality holds here, okay? So therefore, we'll have -1 less than or equal to sine of x and less than or equal to 1, okay? As you can see here, this is basically what sine is, right? It ranges between 1 and -1. It never goes greater than 1, never goes less than -1. So we have found a squeeze theorem, but this is not actually our function here, right? This is just sine of x, right? So why don't we divide our whole inequality by x, right? If we divide our whole inequality by x, we got -1 over x divided by sine x over x less than or equal to 1 over x. So now we have squeezed our actual function between two simpler reciprocal functions, right? And now, if we can calculate the limit as x approaches infinity of h of x and g of x, and they equal the same thing, then we know sine of x over x also equals the same thing, okay? So let's calculate the limit as x approaches infinity of -1 over x, okay? That would equal to, using substitution, that would equal -1 over infinity. Whoops. -1 over infinity. And we know that anything divided by infinity is going to be 0, okay? How about the limit of x approaches infinity of 1 over x? That's the same thing. It'll be 1 over infinity, and we get 0. So those equal the same. So therefore, according to our squeeze theorem, sine x, the limit of sine x over x as x approaches infinity equals 0. So we had to do nothing to sine x over x. We just calculated the limits of these two simpler functions, and we found our limit of our middle function. So that's how you use squeeze theorem to calculate the limits of functions. It doesn't work for all functions. Sometimes you have x squared and you don't know how to contain the range of x squared. Actually, you really can't contain the range of x squared. But the squeeze theory is really useful for these kind of oscillating functions because they have a pertained range that is very easily interpretable and easily understood, right? So the junior tutor, when they set up their bounds for the squeeze theory, they said that sine x over x will always be less than or equal to, or always be greater or equal to 0. And I have a problem with this because I don't think this is the correct bounds for it. And if we were to do a graphing calculator of it, let's say if we do graph calculator, right? So if you were to graph sine x over x, you see here that it does actually, in fact, go below 0. So sine x over x actually never is actually sometimes less than 0. So these bounds actually don't work. So even though, so they set up the squeeze theory or the bounds wrong, but the limit still maintains to be the same. But however, because of the bounds that are wrong, this solution is incorrect. Okay. So. Okay. All right, let's move